could now solve for rho, the resistivity of that conductor. Okay, let's do another problem. A certain light bulb has a tungsten filament with a resistance of 19 ohm at room temperature, that is at 20 degrees Celsius, and 140 ohm when hot. Find the temperature of the filament when it is hot. In other words, this is the resistance at 20 degrees Celsius. That means that is R20. This is the resistance at a high temperature T. So this is RT. What is the relation between resistance at a particular temperature related to resistance at 20 degrees Celsius? RT equal to R20 times 1 plus alpha T minus 20. And you know R20 is given to us, RT is given to us, the resistance at T degrees Celsius is given to us. We need to find that temperature T. Alpha, this is tungsten, so we can go back to our table and obtain the value of alpha. Alpha for tungsten. Now we have RT equal to R20 times 1 plus alpha times T minus 20. Now we know RT, we know R20, we know alpha, therefore we can solve for T. Using all those values, alright, can you simplify this equation and solve for T? I have 1 plus 4.5, look at what I have done here. I have taken this quantity inside the square bracket, that is this, equal to 140 divided by 19, that is 7.37. And now 1 plus 45 times this quantity. Now this one I took from the left to the right, 7.37 minus 1 is 6.37. And what you need to do is distribute this quantity, there you are, T minus 20, see, rather than distributing, T minus 20 equal to 6.37 divided by this number. And that's easy to do it on your calculator. What is 6.37 divided by 4.5 times 10 to the negative 3? You must do it and make sure that you have that value. Or if I'm wrong, tell me about it. So you get T minus 20 equal to 1415.6. And now take that negative 20 to the right side. Therefore T equal to 1435.6 degrees Celsius. You can see simple use of that equation will solve that problem for you. Okay, we will now talk about an electric cell. Now I showed you a simple electric cell. Let's discuss more about electric cell. Now what is an electric cell and how is it made? In order that an electric current may flow continuously, the potential difference between the two plates needs to be maintained. And in the example I showed you, I had a sulfuric acid with copper and zinc electrode. It is the chemical action between the electrodes and the solution, the acid, that builds and maintains that potential difference. Now this can be achieved only if negative charges can be removed from the positive and deposited back in the negative. You see, as negative charges drift from the negative plate to the positive plate, in order to maintain the potential difference, you need to remove negative charges from the positive and put it back in the negative. So this is the external conductor, and you need to do this internally through the cell. And that is what the chemical action in the cell does. This can be done chemically by placing two metal plates in a suitable chemical so that electrons may be removed from the positive internally and deposited back on the negative, so that the charges will now be moving in a closed path. You see, in order to maintain the current, as negative charges keep moving from the negative to the positive externally, you need to move the electrons from positive to negative internally through the cell. Then only the electric current will keep on flowing. Now, here is what a situation I showed you. This is the zinc, that is the negative plate. Copper, that is the positive plate. When you connect them externally, negative charges will move from zinc to copper externally and from copper to zinc internally, so that the potential difference between the two electrodes are maintained. Now, such an arrangement is called an electric cell, which very often people call a battery. Now remember, a battery is a collection of cells. In fact, a collection of anything can be called a battery. Is that right? Have you heard of a battery of soldiers? Yes. So battery is actually a wrongly used word. It's the electric cell is the correct word. The conducting plates are called electrodes. Zinc is the negative electrode and copper is the positive electrode, and the solution, the acid in there, is called the electrolyte. So the basic parts of a cell has electrodes and electrolytes. Now, a simple cell can be produced by dipping a copper plate and a zinc plate in dilute sulfuric acid, as I showed you. And a cell is represented by the symbol. Look at the symbol for the cell. The positive pole of the cell is the long thin line, and the negative end of the cell is a short thick line. Now don't confuse it with the capacitor notation. What is the symbol for a capacitor? Just two parallel lines. Alright? Okay. When the negative pole of the cell is connected to the positive pole, electrons drift from the negative to the positive externally through the conductor, and from positive to negative internally through the cell. If the closed chain is broken, the current will cease to exist. The chemical action between the electrode and the electrolyte, what does it do? What is a cell? Now here I have a cell in here. This is a cell. There is a chemical inside, and there is a positive electrode and a negative electrode. Now what does the cell actually do? The chemical action between the electrodes and the electrolyte will build and maintain a potential difference between the two plates. So there is a potential difference between the two plates or the two electrodes, the positive electrode and the negative electrode. I can now measure it by using a voltmeter. If I connect a voltmeter across the cell, that voltmeter will measure that potential difference, which is built and maintained by the chemical action. And this potential difference, which is built and maintained in the cell, is actually called the electromotive force, in brief, EMF of the cell. So a cell has an EMF, electromotive force. In other words, when the cell is connected externally by a conductor, what is the motive for electric charges to flow? is provided by that potential difference. That is why it is called the electromotive force. It motivates the electric charges to move. So the cell has an electromotive force. We will represent it by E. And what is the unit for measuring electromotive force? It is volt, because it is a measure of the potential difference. Alright, when the cell drives a current in an external circuit, the current also passes through internally through the cell. Now, therefore, what does this E really represent? The electromotive force. The electromotive force can be considered to be the total energy the cell makes available for electric current to be driven externally through a conductor and internally through the cell. That means when current flows, energy is used to drive current externally through the conductor and also internally through the cell. The electromotive force is actually the sum of the two energies. Energy that is available to drive current externally and also to drive current internally. Now, only the remaining, that means, so part of that energy, part of the electromotive force is used in driving current internally through the cell. That means only the remaining is available to drive current externally when there is a conductor connected externally. The potential difference between the poles of a cell then becomes less than E. I want you to understand this very well. I will demonstrate that in a minute. You see, if you now connect this cell to a voltmeter, it will measure the actual EMF of the cell. But if you connect a conductor across the cell, which will then allow a current to flow, the voltmeter reading will fall. The voltmeter reading will be less than the EMF. Why? Because the voltmeter then will read the potential difference across the conductor, which is a measure of the energy used in driving current in that external conductor. Why it is less? Because part of the EMF is used in driving current internally through the cell. Okay. Now, potential difference can be measured using a voltmeter. Now, let me see if I can demonstrate that to you before I draw the diagrams for you. Here I have a cell. Actually, this is a battery. It's a combination of some cells. It's got its positive pole, negative pole. I'm going to connect it to a voltmeter and see what the voltmeter reads. I'm connecting it to the voltmeter. I want you to watch what the voltmeter read. Now, what does the voltmeter read? It's read 5.92 volt. Now, what does it tell you? This is the EMF of the cell. When you connect a cell directly to a voltmeter, what the voltmeter reads is the EMF. Now, I'm going to connect the cell to an external conductor. You are familiar with this. Now, I have chosen 1 ohm. This is on now. Everything else is off. So, if I now connect this cell, I think the positive and the negative, I'm going to connect it to here. That means the cell is going to drive a current through that external resistor. Now, see what happens to the voltmeter reading when I do that connection. Well, I hope I will be able to keep them there when I do the connection. Alright? So, hold your breath. I'm going to make this connection now. That is going to go to one end of this resistor.